Welcome back. In this lecture, as part of our last lecture on the module Contextually Constrained Deep Learning, we're going to talk about approaches to solve constrained learning problems. Not only we want to, let's say, minimize the training error, but also we want to make sure that some context which leads to, let's say, a specific constraint or another kind of an objective is also satisfied to some degree. Okay, so we talked about numerous learning setups in previous lectures, where we effectively ended up having a training problem like equation 1, where we want to, let's say, minimize the average loss over the training data plus some regularization term. And this regularization term, for instance, could arise from the context of ensuring the model does not memorize some specific sample. It could arise from the concept of robustness, or it could arise from some other considerations. Maybe energy considerations, maybe safety constraints, maybe fairness, etc. Okay? But more abstractly, we had, let's say, again, like two terms, minimizing the average loss plus some regularization term. And lambda here was basically our regularization parameter. It would indicate how much we want to enforce the regularization term. If lambda is equal to 0, it means that we completely ignore this function hw, which represents our regularization. And as I increase lambda, I'm putting more and more emphasis on satisfying this regularization term, such that at the limit when lambda goes to infinity, I completely ignore the training objective and only focus on making sure that the regularization term is satisfied. Okay, so therefore this gives rise to this question that how should we determine lambda? Okay, so in practice, what's the best lambda to use? And that basically determines how much you want to enforce your context. Okay, or another way to pose this question is, what if we want a certain condition to be satisfied in a very, very strong sense? Intuitively, when we include this regularization term, we are ensuring a constraint is satisfied in a soft manner. But in a lot of applications, we want to make sure that the constraint is satisfied in a hard manner. Okay, so for instance, when we are training a deep learning model and we want to make sure that certain degree of fairness is satisfied, we may want to include that fairness as a constraint. And then maybe we have a specified or pre-specified fairness degree that we want to make sure that no matter what happens, no matter what the performance of the model is, that condition is met. Or in the context of memorization, perhaps we have a number of data points in our training data that we want to make sure that the memorization score of our model for them is below some threshold, to make sure that the model does not memorize them, maybe because those are highly critical data points that we want to preserve their, let's say, privacy. Okay, so these kind of questions therefore lead to a general constrained learning setup, where we want to, let's say, minimize the training loss such that h of w is less than some threshold. Okay. Now, many times in the context of machine learning and deep learning, the constraint function h of w itself can be a stochastic function. And by stochastic function, I mean that, for instance, you can write it down as some form of expectation, where the expectation here is with respect to a different source of randomness with a potentially different loss function or per sample loss function L tilde. Okay, and I have an example of that in the next slide. Okay. But before that, I want to mention something here, that without loss of generality, we can set this threshold to be 0 by redefining our constraint function to be, let's say, h of w minus tau as opposed to h of w. So for the rest of the lecture, we just assume that tau is 0. Therefore, our constraint learning problem is to minimize the training loss such that h of w is less than 0. Okay. Now, beyond the examples that we saw in previous lectures, for instance, again, the context of low memorization, robustness, etc., I want to point out two other applications where they lead to a constrained learning problem. Okay, and one of these examples is the famous multi-class Newman-Pearson classification. Okay, so we talked about classification a lot in this course as a running example, where we wanted to learn, let's say, a deep learning model, a parametric model that can classify certain data points correctly. For instance, we have cats and dogs images, so I want to learn a model that can classify the images according to whether they are image of a cat or image of a dog. Okay, so binary classification, for instance. Multi-class classification means that we have multiple classes. For instance, 10 classes in the case of the MNIST dataset, or CIFAR 10 dataset, or 100 classes in the case of the CIFAR 100 dataset. Okay. Now, in those examples of classification we basically wanted to minimize the average loss over the entire training data. That meant that we did not prioritize performance on a specific class over other classes. In Newman-Pearson classification, on the other hand, we do have a prioritized class. So we want to make sure that the loss for that class is as small as possible. But naturally, that could come at the cost of other classes. So we impose constraints to make sure that the model performs relatively well on other classes as well. Okay, so in particular, that leads to the following training or constrained learning problem, where we minimize the loss of the first class such that the loss of all the other classes are below some threshold. Okay, threshold tau I. Okay, so again here, Fi is the loss of the each class, and here we are prioritizing class 1. Okay, now again, each of these Fi's is to be thought to be a stochastic function, meaning that it can be written as some form of an average. F1 is just the like the average loss over the examples belonging to class 1. F2 basically is an average loss over all images or data points that belong to class 2, etc. So therefore, if we associate classes to different distribution, this is like saying that each of these Fi's is a stochastic function with a different source of randomness. All right, so that's one example on that sort of indicates the importance of constrained learning. Another example is the famous applications of physics-informed neural network. So the idea here is that we want to learn a deep learning model that can approximate the solution to a differential equation. Could be an ordinary differential equation or most notably a partial differential equation. So here's the idea, right? You have a bunch of training data points, okay? So let's say xi's and the corresponding observation yi, and then you have a bunch of other data points that you want to make sure that the model or the physical constraint modeled by this differential equation is enforced. And we're going to use this as a constraint for our learning problem. So we're going to minimize, the training loss, make sure that our model is something that fits the training data well, on average, such that some physical law is enforced. Okay. Again, so here, this D physics, you can think of it as some distribution or a set of data points that are sampled from our domain, where we want to make sure that the physical constraints, for instance, the differential equations, are enforced. Okay. So this notation here is basically called the differential operator, and that is a quantity that represents the governing laws of the system. For instance, this could represent a partial differential equation. So by this, what we are saying is that we want to basically learn a model that fits the training data well, and also is a solution to a differential equation, such that physical law is basically obeyed. And we're going to capture that by introducing this constraint into our learning problem. All right. So therefore, there are lots of applications where, in addition to having an objective function in our learning problem, we also have a constraint, so that we have to care about. So abstractly, we can think of these kind of problems as this. So we are minimizing a stochastic function subject to the constraint that h of w, our constraint function, has to be less than or equal to 0. Okay. Now, how can we solve this? Okay. So a natural thing to do is to try to include the constraint as part of the objective. Okay. And in particular, we can do this and get an equivalent problem by leveraging the indicator function of the constraint. So in particular, consider this indicator function, which says that if h of w is less than or equal to 0, meaning that we have a solution w that satisfies the constraint, it's a feasible solution, the indicator function is equal to 0. On the other hand, if the solution is not feasible, meaning that h of w is strictly larger than 0, the indicator function is equal to infinity. So then, if we include this as part of our objective, we're going to get an equivalent problem. Okay. So in particular, if we are able to solve this, we're going to find solutions that are feasible and also minimize the objective. Okay. So this indicator function, in some sense, shows our amount of displeasure regarding the violation of the constraint. Okay. So in this case, where we are using this indicator function and we are ensuring that the value of the function is infinity if the constraint is violated, we are utilizing maximum displeasure. So we are using maximum displeasure, and this leads to an equivalent problem. But the catch is, it may not be an easily approachable problem, given the not so nice structure of this indicator function. So therefore, one thing we can do is to sort of use softer displeasure mechanisms. Instead of using this indicator function, for instance, we can use a linear displeasure function, a quadratic displeasure function, or a combination of the two. Okay? And in particular, these are approaches that have been explored significantly in the literature and have led to very elegant algorithms and theory that I'm going to very briefly discuss some of them in the next few slides. Okay. So in particular, utilizing, let's say, a linear function, a quadratic function, or a combination of the two leads to penalty-based as well as the Lagrangian-based formulations. All right. So in the penalty-based approach, we typically use a quadratic function to sort of approximate this maximum displeasure idea that we talked about in the previous slide. So in particular, what we do, let's say we take the original loss and then we augment it with the penalty function that depends on the constraint. So in particular, our penalty function is some, let's say, rho. Again, it's a quadratic function. So it's rho divided by 2 times h w squared. We actually don't use h of w squared because, remember, our constraint was h of w less than or equal to 0. So we only penalize when h of w is positive. When h of w is negative, we don't need to penalize because the solution is actually a feasible solution. That's why inside of this quadratic, we have this sort of this operator or this function, the plus operator, which basically is going to be the maximum of, let's say, h of w and 0. So this indicates that if h of w is positive, we are in violation of the constraint, so we want to penalize it. On the other hand, when h of w is negative, we are not in the violation of the constraint, so there is no need to penalize it and include it as part of the, let's say, the objective. So this is called the penalty-based method, and it relies on this penalty parameter rho. Now, you can try and solve this problem, right? So it is only a function of like w, okay? And one question is, what's some theoretical results for this algorithm? In particular, if I use an iterative method to solve this, maybe something based on the the gradient descent or some more complicated algorithmic idea, can I find a solution that is suboptimal or near optimal? And under certain assumptions, we can actually show a convergence of methods based on this idea, but many of them require to use an adaptive schedule of penalty parameters rho that are increasing. So in particular, we require rho to increase with every iteration and approach infinity to ensure that we find a feasible solution. So this basically is not very desirable in practice. So in practice, we don't like working with very, very large numbers or very, very small numbers due to numerical instability, and this has sort of led to other algorithmic solutions. For instance, instead of the quadratic penalty, you can include the linear penalty, or you can include both the linear penalty as well as the quadratic penalty. And incorporation of the linear penalty leads to ideas based on the Lagrangian method. Okay, and the name comes from the name of the Louis Lagrange, the famous mathematician who came up with this idea when he was working with the calculus of variation and this principle of least action in classical physics. Okay, so what's the idea? The idea is actually, as I mentioned, you include a linear penalty. So you have your original loss plus some lambda times the constraint, where lambda is larger or equal to 0. This again captures our amount of displeasure. Okay, if we are not in the violation of the constraint, then lambda can be 0. On the other hand, when h of w is positive, meaning that we are violating our constraint here, then given that lambda is positive, we are adding a positive term to the loss function. So it means that we are penalizing the fact that we are violating the constraint. Okay. Now, another question similar to the last one that we pose and kind of answer for the penalty-based method is about the role of lambda. Okay, and this is something we're going to talk about in the upcoming slides. Now, another approach is that we can combine these two together, include both the linear penalty as well as the quadratic penalty, and this is referred to as the augmented Lagrangian method. Okay. So we have the linear term here, the quadratic term, and then if you complete the quadratic, you can and get rid of the constants, which are not a function of w, but could be a function of, let's say, rho and lambda. We can equivalently write this down in terms of, let's say, again, the original loss that we want to minimize plus a quadratic penalty that is kind of shifted. Okay, so and that depends on this parameter lambda, which is referred to as the Lagrange multiplier, or the dual variable. Again, it matters what rho is and what lambda is. So we're going to talk about the calculation of lambda, but one nice benefit of the augmented Lagrangian method compared to the penalty-based method is that for certain classes of problem, rho does not need to increase to infinity. So in some sense, this method is much more numerically stable than the penalty-based approach. So this is a quick overview of some of the existing ideas when it comes to handling constraint layering problems. Now, in the next part of the video, we're going to talk a little bit more about the Lagrangian idea, and then we're going to talk about some approaches to solve these kind of problems that I've stated here. I'll see you in the next video.